Welcome back, class. In today's video, we're going to talk about the effect of temperature on the rate. So what we've talked about so far is concentration, right? How concentration is affected to the rate, how concentration changes over time based on the kinetics of a reaction. And in all of those, right, we showed what we called the rate constant. And so this is that proportionality constant that is unique to a given reaction. And we called it constant, right, because it was constant no matter what the concentration was, right? It doesn't change, right? So, and every time we did an experiment, if we use a different initial concentrations, right, the rate constant is the same, right? And we saw that when we could do our plots, and we could get the rate constants based on those various plots from our integrated rate laws. Now, one thing that does change or does affect the rate constant is the temperature. So the rate constant is temperature dependent. So as long as we're operating at the same temperature, the rate constant is constant. And this is oftentimes when you look at kinetic data, why they will specify what the temperature is in the reaction, because that will affect what the rate constant is. Now, the sort of key equation that we'll be looking at as we look at the effect of temperature on the kinetics is something called the Arrhenius equation, or sometimes called Arrhenius equation. And it shows this relationship. So one way to write this, and this is sort of the way that I will typically write it, you may see it written in different ways, in various sources, but the way that I will typically write it is this way, where we have the rate constant for our given reaction equals this capital A here, which is something called the frequency factor, and we'll talk about some of these things in more detail as we go through here, times an exponential, right? So this is an exponential factor, so an e to the x, if you will. So one way that you might just write that out would be, it's an e to the x, like if you're thinking about your calculator, right, as opposed to 10 to the x, right, it's e to the x, right, it's an exponential. Now in this case, the x here is negative this value called E sub A, or what we call the activation energy, divided by RT. Now let's look at what sort of each of these parts are in our equation. So first of all, T, right, is our temperature, importantly in Kelvin. Right? R is the gas constant, right? We've encountered this R before in our first semester when we talked about the gas laws, right? And the particular version of R that we're using is the one that has energy units. And so the particular value is 8.314 joules per mole Kelvin. Hence why we need our temperature in Kelvin, right? So that we match up our units here. Now, again, A is the frequency factor. Now, in sort of basic idea, and again, I'll talk about this a little more detail, it's the rate the reactant energy approaches the activation energy. So it's sort of how often the reactants try to make products, if you will. Now, E sub A, again, is this concept called activation energy, right? And this is the energy barrier for the reaction to occur. So it's the minimum energy needed to start the reaction. So every reaction has an activation energy, an energy that's necessary in order for the reactants to react, to become products. So as we go through this section, we're going to look at these different factors in more detail and look at these concepts in more detail. So let's start a little bit by looking at the activation energy. So if we come back to our reaction diagram, so you might remember these from last semester, where we used them to illustrate exothermic and endothermic. But they looked maybe a little different So this is an exothermic one. So it might have looked just simply like this, where we had our reactants and our products, right? And our products were lower in energy, and so that's why it was exothermic. Or we could also have endothermic, right? Where we had, something that looked like this, where we had our reactants and our products. And our products were higher in energy, so we had to gain energy, so it's endothermic. So we had exo and endo. So this is that same diagram, but now we've got a little more detail. So this was sort of an approximation, right? In reality, every reaction, no matter it's endothermic or exothermic, has this hump they have to get over. And the height of this hump, right, is what we call the activation energy. So the bigger this hump is, the harder it is for the reactants to become products, if you will, right? Because they have a bigger hill to climb, a bigger barrier to overcome. And that's what we mean by the activation energy. Now, the species that forms at the top of this barrier is called the transition state, or sometimes called the activated complex, right? And it is some chemical species that is partway between the reactants and the products. So it is some sort of species where we've started to break the bonds in the reactants, make the new bonds that are going to form in our products. These are high energy species, right? Not very stable because of the partial bonds, right? And again, they're only transitional, right? So they're very hard to isolate. Sometimes we can identify these spectroscopically using different techniques, right, during the course of the reaction, but they don't hang around. Okay. So there's a little bit of overviews. Let's look at an example. So one of the examples given in the book is this isomerization of what we call methyl isonitrile. So this is a very simple reaction where we have one reactant and it is undergoing this, in this case, isomerization to form our product. So our reactant here is the methyl isonitrile here, where we have the CH3 group bonded to a nitrogen and triple bonded to a carbon. Now the product here, notice the difference is the methyl group is now bonded to the carbon instead of the nitrogen. Right? So in essence, the carbon and the nitrogen have swapped places, or this triple bond has flipped around. So we can see we start out here. Now we have to barrier here. So we have our activation energy, and at the top, our activated complex, again, is somewhere in between having this carbon bonded to the nitrogen, like it would here, and the carbon. So it's, there's a beginning of the rotation here of this triple bonded CN. So it's starting to break the carbon-carbon bond, starting to break the carbon-nitrogen bond that would be here, and starting to form the carbon-carbon bond that's going to exist in our product. So starting to break this bond and form this bond in this high-energy activated complex. And so we get up to here, and then we fall down to our product here, which is lower in energy than our reactant. Right? So this makes this reaction exothermic. And two different energy values that you could get if you had numbers on this process, right? And we don't want to get these confused. We have the enthalpy of reaction, which is something that we've talked about before, right? Which is the energy between the reactants and the products. Right? So in this case, the products are lower by a certain amount of energy, so it's exothermic by this amount. Now, the height between the reactants and the transition species, or the height of this hill, right? This is a different energy value, right? This is the activation energy. So we don't want to get those two things mixed up. They're not the same. We have the enthalpy of reaction, and we have the activation energy. Okay, so that's a little bit about the activation energy. That's one of the terms in our Arrhenius equation. So at this point, let's look a little bit at that other term that was new, the frequency factor. So for that particular one, right, the frequency factor is a look at that reactant, right, where we have this carbon-nitrogen bond forming that activated species. Now, in this particular, they call this rotation a wag, right? Sort of like wagging a tail, right? So where we start this rotation. So the idea is we're going to start this rotation a bunch of times, right? But it's not always going to complete itself, right? There has to be enough energy available or enough energy involved to complete the wag, get up here, and fall over. Right? Now, the frequency factor is essentially telling me how many attempts or the number of wags, right, that occur at any given time. So it's the number of molecules that begin to form that activation complex, or the number of molecules that try to undergo this transformation. So how many attempts do we make to get over the hill? That's the frequency factor. No, so in essence, it doesn't tell us how many times we're actually successful. But one might conclude that the bigger the frequency factor is, right, the more that we're going to go over here, because, it's like anything, the more attempts that you make, you're likely to get more successful attempts. But, so the frequency factor, again, is the number of times the reactants approach that activated species. Okay, so if we remember back to our Arrhenius equation, right, the frequency factor is one part of the right-hand side of our equation, right? So really we can break it down into two parts. We have the frequency factor multiplied by this exponential factor. And part of that exponential factor is the activation energy, and the R, and of course the temperature, right? And this is really in the exponential where the heart of our temperature dependence comes on, because this is where the effective temperature is going to be shown, is in the value of this exponential. So the exponential factor is going to be a number between 0 and 1. Right? So depending on, the value of this negative EA over RT, right, we're going to get a value for the exponential between 0 and 1. And it represents the fraction of molecules with sufficient energy to make it over the energy barrier. So if we think about this a little bit more, right? So we take our 2 points. So we have A here, right? Remember, A is simply the number of attempts. Where the exponential factor now is the number of attempts with enough energy to form products. So in other words, we have the total number of attempts times the number of attempts that actually have enough energy to be successful. That's where we get the rate constant from. So A represents the total number of attempts. The exponential represents the fraction of those, if you will, right? Is it 0% or is it 100%, right? So it's the fraction of those that have enough energy to get over the barrier to be successful. So you might think about the higher the barrier, right? The more energy you needed, right? The larger the activation energy, the fewer molecules that are going to have enough energy to be successful. So your exponential factor is going to be lower, right? So you may have a big A, but if your exponential is low, then you're not going to have very many successful reactions. So how does temperature play into here? Well, let's just think about it. So what happens to this fraction, this E over RT, if we change the temperature? Now, think about activation energy as a constant, right? So the activation energy for a reaction is constant, right? It doesn't change. So we have a certain activation barrier that we have to meet. So how does changing temperature work here? So let's just say I make T bigger. So making T bigger makes RT bigger, right? So it makes, so if I raise T, if you think about that, then RT becomes bigger. And so since RT is on the bottom of this, as the bottom of this fraction becomes bigger, then the whole fraction, negative EA over RT, becomes smaller. Now, what happens when negative EAT over RT becomes smaller? Well, to think about that, we have to think about what happens to our exponential. So let's just do a thought experiment here. And let's just say our negative EA over RT equals 0.5. Then that means our e to the x, right, our exponential factor, equals 1.65. Okay, so if I increase the temperature, then this is going to get smaller. So let's say that it equals let's say it equals 0.25. Now your e to the x equals 1.28. So as this value gets smaller, your exponential gets smaller. Here, sorry, I need to rewrite this a little bit for you, I think. I know what I forgot to do here. Sorry, made a little mistake here. So this is why you got to be careful here. Forgot the negative sign. So if EA over RT is 0.5, then that means we have negative 0.5 and negative 0.25. So if we take e to the, let's erase all this here. So let's say we have e to the negative 0.5. So that's going to be, whoops, so let's get my pen back here. Equals 0.61. But if I have e to the negative 0.25, we have 0.77 or 78. So our exponential factor has gone up, right? So as this gets smaller, right? So this value gets smaller, right? Our exponential, this part gets bigger, right? Which means the number of attempts with enough energy gets larger, so we get more product. Right? So this is why typically for most reactions we see that as we increase the temperature, we increase the number of molecules with sufficient energy to overcome the energy barrier. Right? In other words, our exponential part of this equation gets bigger. Which means if one part of our, either if our exponential factor gets bigger, that means our K is going to get bigger. Our rate constant is going to get bigger, which means our reaction rate gets faster. Right? Increase the rate constant, we get faster reactions. So typically what we see here is we have higher temperature, we get a higher rate constant, which leads to a faster reaction. So increasing the temperature will typically increase the reaction rate because of what the effect of temperature is. And we can show that mathematically by looking at how it works in our equation. Okay, so let's look at it a little bit differently here, and let's just look at the graphical. So let's just say that I have two temperatures and I take the fraction of molecules over energy. Now, at some point, we have our activation energy, right? So if our molecules have this enough energy, they're going to have enough energy to get over the activation barrier. And what we can see here is if we look at these two plots, that if I'm at a higher temperature, my curve shifts to the right. So so in other words, I have a larger percentage, right, the area under the red curve, right, a larger fraction of my molecules now are beyond the activation energy or have enough energy to overcome the barrier. So again, just showing graphically here, at a higher temperature, more molecules have enough energy to get over the barrier. Or in other words, our exponential part of our Arrhenius equation has gotten bigger. Faster reaction. Okay, so if we look at the Arrhenius equation, now another way that you will see this written out is a linear version of the Arrhenius equation. Now again, typically we work with it in that other version, but we can transform this into a linear equation. Now, I'm not going to go through the mathematics that we used to get here. You notice we got rid of the exponential. Those exponentials become natural logs when we go through and modify the reaction. Now, the algebra of this is shown a little bit more in the book, but what I'm more interested in is just the new form of this Arrhenius equation. So it's the same equation, but we can use this form in order to plot, right? Notice this is in the form of a line, And what this is telling me is that there's a linear relationship between the natural log of the rate constant and the inverse of the temperature. So, in other words, as the temperature goes up, 1 over T gets smaller, the natural log of K gets smaller. So there's a relationship there between the inverse of temperature and the natural log of the rate constant. Okay, so this is a useful equation, but, and we can use this if we have the data. We could, of course, use this to get the activation energy, right? From the slope, we could use it to get the frequency factor from the y-intercept. Okay. But this, frankly, is not the most useful way to use this equation, right? This is great if we have a bunch of experimental data, and you'll see an example in the book where they do this, but gathering this data is terribly difficult, right? It means you have to run the equation very controlled at a lot of different temperatures and plot the rate constant at all these different temperatures. So it's not easy data to gather, right? So our application of this is really going to be a more abbreviated application where we can rearrange this equation or to allow us to work with just 2 temperature points. So in other words, to look at how the rate constant changes over temperature using just 2 data points. So this is what we call a 2-point equation. And so you can go from that previous equation, again, you can go through a little bit of an algebraic manipulation to get to this 2-point equation. And again, you don't have to memorize this equation, you just have to know what it's used for. And so we can see here we have 2 different temperatures, 2 different rate constants. So this kind of equation can be used, right, in a lot of different ways, but commonly if we know what the rate constant is at T1, we can say, okay, what if I make the temperature T2 here? What if I change the temperature? What happens to the rate constant? So we can find K2. Now, you could, of course, also be given 2 rate constants and find a temperature, but we're going to solve for one of these 4 values here. Now, the other way that we can use this is that we could also use this as a way to solve for the activation energy, right? So I can measure what the rate constant is at only 2 temperatures here, and I could then plug all that data in and calculate the activation energy. So again, that's another way that this 2-point Arrhenius equation can be used. All right, so I'm going to end this video here. In the next video, we're going to take a more theoretical look at the frequency factor. And we're going to dive into a little bit more about what makes reactions work.